Hello, everyone. In this work, we propose a low-cost portable system for acquisition and modeling of ice hockey stick shape deformation from player short videos. Ice hockey is a high-paced, equipment-heavy game. The hockey stick market is almost $300 million alone. A perfect hockey stick is vital for a player's success. Literature in the area suggests that sticks well tailored to a given player can help them with executing much faster and more accurate shots. So how can this be done to tailor the player specification to the stick? So one way to do that is to perform a 3D reconstruction of the stick during a shot. This could help us extract invaluable information about the stick bend, the velocity, and so on and so forth. But there are a number of challenges to accomplish that. So hockey shots are very high-speed motions, and the hockey stick is a relatively thin piece of geometry immersed in a relatively large capture volume. In addition, because of the speed of the shot, the images are generally dark and noisy. So this has been done in the past using motion capture technologies. So you place a number of infrared cameras in the scene and you attach them to the hockey stick and then you track them. And this partially can solve the problem, but this is a non-portable setup and a very high-cost equipment. And not to mention about the intrusive nature of the markers. Another way to address this problem is to use structure from motion. So you position multiple cameras, color cameras, and we can reconstruct the geometry of the scene, which includes the stick, the person, and the rink. The problem is that this doesn't get us very far. We still have to be able to separate the stick and to figure out the correspondence points from frame to frame, where each point on the stick goes from one frame to the next. For that, one can use templates, and templates have been used in the past for this kind of reconstructions. Some previous methods, they use RGBD cameras. Unfortunately, they are very slow. So the hockey stick shots are very fast in comparison, so they cannot capture correctly. The second problem is that orientation of the hockey stick keeps changing rapidly, and this makes it different for some of the monocular approaches that we have seen. In this work, we propose a complete system, software pipeline, and hardware setup, which is portable, cost-effective, and non-intrusive. There's no marker that has to be attached anywhere. In the next slides, I will present this method in more detail. So for the acquisition and setup, we use 2 global shutter vision color cameras and a temporal synchronization box, because temporal synchronization is very important given the speed of the motion. We are able to acquire at about 275 frames per second at a relatively low resolution of 672 by 608 pixels. We had to trade off spatial resolution for temporal resolution in order to accurately capture the motion of the stick. So the first step is to reconstruct, to use a stereo reconstruction step from 2 images. One of the images showing here at the top left, and the point cloud obtained is showing at the top right. This we use the Achisoft Metashape software. The problem is that this reconstruction includes the stick, the floor, and the person. So we need to be able to prune to only allow the points which are on the stick. We do this in 2 stages. The first stage is the motion-based pruning. So we look at the optical flow, and we only keep the pixels that have enough motion, and this is showing on the top middle image. Still, this pruning is not enough, as you can see at the bottom left, because in addition to the stick, we still have some points on the body, because the body also moves pretty fast. So a secondary pruning is done by fitting a template. So first we fit the template rigidly, and we use the template from the previous frame. And by doing that, we already can prune most of the points outside of the stick. The next step is template deformation. So we have the template position, but we have to be able to match this template to the point cloud. But if we match it directly to the point cloud, the results showing here the top row are not very good, because the point cloud is very noisy and we get relatively strange deformations. Instead, we propose a novel method where it's using the medial axis to drive the deformation process. So we fit a quadratic curve to the medial axis of the point cloud, and we fit the medial axis of the stick to the medial axis of the point cloud. You can see here the bottom right final result. So here we describe this in more detail. So you can see the points on the medial axis of the point cloud, and you can see that there are some kinks in it because of the noise in the point cloud. So we use a ransack procedure to select the points only on the stick. So we remove the points on this procedure removes the points on the shaft as well as the noisy points along the shaft. You can see here two views. The second view is better to illustrate the noise in the medial axis. And given the remaining points, we fit a quadratic curve, showing here in green. And we use this quadratic curve to deform the template mesh, and we use a co-rotational FEM model for this deformation. So here are some of our results. So this is an example of a slap shot. And you can see that the stick bends quite a lot, and it even has a slight end backward bending at the very end because of the momentum of the stick. In the paper, we have provided also some quantitative evaluation of our method. This is the second shot. This is a wrist shot. Both of them are done to reduce speed. So this is one of the original cameras, and this is the initial reconstruction with the template overlaid on top. In the paper, we provided an accompanying video. In the paper and in the accompanying video, we have more examples. So in this work, we have presented a complete pipeline for 3D reconstruction of deformable hockey sticks. It is low cost, it's portable, it's non-intrusive, and it is an end-to-end system that it goes from the hardware all the way to the software. And the results are comparable to the motion capture data. And also, but instead of tracking only a sparse number of points on the stick, we are actually reconstructing the entire stick. So further analysis of the option can be done. There are some limitations. So we do not deform the blade of the stick because the geometry is quite noisy. So we leave it rigid. And this is a problem because in reality, the blade bends as well. And the second problem, the second limitation is that actually we need to have a relatively decent point cloud to start with. So in the future work, we want to address these issues, specifically the blade deformation, and we want to continue working furthermore to incorporate this deformation into the stick analysis and a stick recommendation system. Thank you very much for your attention.